Every piece of information inside a computer, every photo, text document, and video, is ultimately represented as a physical sequence of binary digits, or bits. As datasets grow exponentially, this raw physical footprint hits hard limits. Storage arrays fill to capacity, and transmission speeds bottleneck under the sheer weight of the data. To alleviate these bottlenecks, computer science relies on data compression, the systematic process of shrinking a file's digital footprint so it occupies less space and moves faster across networks. There are two distinct algorithmic paradigms available to solve this problem. The first is lossy compression. This method achieves smaller file sizes by permanently discarding minor details. When you see a highly compressed, pixelated JPEG, you are looking at lossy compression. That missing visual data is gone forever. The second paradigm is lossless compression. This approach reduces the overall file size while preserving the exact original sequence of data. When a losslessly compressed file is opened and decompressed, every single original bit is perfectly recovered. Zero information is sacrificed. The gold standard foundational algorithm for achieving this lossless state is known as Huffman coding. Mastering lossless compression secures perfect data fidelity within strict physical limitations, allowing massive datasets to be stored and transmitted efficiently. Standard computing normally operates on a baseline assumption. Every character in a file receives a uniform fixed-length code. Treating a highly frequent character with the exact same bit weight as an extremely rare character creates immense structural waste. By analyzing the statistical frequency of characters in a specific document, we can optimize the storage space. This table maps a simple data set. The character A appears 5 times, B appears twice, and C appears only once. Instead of using a fixed-length sequence, we deploy variable-length logic. We assign the shortest possible code, a single bit, 0, to this highly frequent A. Because A dominates the text, shortening its specific code immediately saves the bulk of our required storage space. We then assign progressively longer binary codes to the rarer characters. Even with longer sequences for B and C, the overall footprint shrinks dramatically. This calculated asymmetry is the core underlying logic of Huffman coding. Frequency-driven variable codes transform a rigid storage block into a highly optimized data array, custom fit to the exact file it represents. Shifting to variable-length codes introduces a fatal vulnerability during playback: decoding overlap. Without fixed lengths, a computer scanning a continuous stream of bits struggles to identify exactly where one character ends and the next begins. If the code for A happens to be the exact starting sequence for the code of B, the machine faces a critical ambiguity. It cannot make a definitive translation. Huffman coding bypasses this catastrophic failure by enforcing a strict mathematical mandate. This mandate is known as the prefix code. The rule of the prefix code states that no binary code in the system can be the exact starting sequence of any other code. In practice, as the machine reads the incoming bit stream, it never has to guess. The moment it detects a complete, valid code, the sequence naturally terminates and snaps to its assigned letter. This ensures that every single encoded message has one and only one valid translation. The prefix rule is the essential architectural constraint that allows a continuous stream of variable-length bits to be parsed with zero ambiguity. This presents a logistical challenge, systematically generating a perfect, non-overlapping prefix code for any given dataset. This diagram illustrates the specialized data structure utilized to solve this, the Huffman tree. It operates on a strict binary branching logic. Every path branching to the left is assigned a 0. Conversely, every path branching to the right is assigned a 1. The critical placement rule of this tree is that actual characters are locked exclusively at the absolute bottom endpoints, known as leaf nodes. Because a character only exists at the absolute end of a path, it is mathematically impossible to pass through one character's code to reach another. This contrasts sharply with the internal junction nodes above them. These internal nodes do not contain characters. They display the combined numerical sums of the frequencies branching below them. These internal nodes merely store statistical weight, acting as navigational signposts for the decoding process. The Huffman tree functions as a geometric rule engine, physically forcing compliance with the prefix rule. By merging lossless compression, variable length frequency mapping, and strict prefix geometry, Huffman coding achieves extreme efficiency. This specific architectural logic acts as the foundation for the archival files you use every day, like zip formats and PNG images. We are left with one final question. Given a massive dataset, how exactly does the computer know how to build this optimal tree from scratch? The tree's construction is governed by a greedy algorithm. It repeatedly hunts for the two lowest frequencies in the set and merges them. Fusing these elements builds the tree upwards until a single root remains. Making the best local choice at every single step logically guarantees the most optimal global compression for the final dataset. In the next module, we will execute this algorithmic process directly, building the priority queues and mapping out the tree entirely from scratch. Huffman coding demonstrates that optimal data compression requires rigorously mathematically reframing information to reach its absolute theoretical minimum size.